Welcome to the Breakthrough Broadcast, a podcast about innovative STEM solutions to real-world problems. From emerging technologies to practical research, Drew Reck explores how science, engineering, and bold thinking are shaping the future.
Hi, I'm Drew, and this episode is about building blood from the ground up. Imagine you're on a remote highway. A car crashes. A passenger is bleeding out. The ambulance is 30 minutes away, and there's no blood, no transfusion kit, no hospital. But then, a responder pulls out a small vial of powder, adds water, injects it, and just like that, oxygen flows through the patient again. Their life is no longer ticking down by the second. That's the promise of artificial blood. For decades, scientists have chased a deceptively simple goal: to create a blood substitute that's shelf-stable, universally compatible, and safe to use anywhere, from battlefield med tents to lunar missions. But real blood is complicated. It doesn't just carry oxygen, it manages immune responses, regulates pH, and transports nutrients. Additionally, red blood cells are uniquely shaped, flexible, and biochemically active. Still, researchers are getting closer. Today, we're diving into the science, the breakthroughs, the setbacks, and the race to bottle blood without a donor. Blood donation saves millions of lives every year. But the system isn't perfect. Supplies run low, shelf life is limited, and not everyone can accept every type. In emergencies, especially in remote or conflict-stricken areas, the right kind of blood simply may not be available in time. Even in well-stocked hospitals, matching blood times take time and care, and stored blood begins to degrade within weeks. Artificial blood, also known as blood substitute, isn't about replacing the functions of real blood. It's primarily focused on one mission: transporting oxygen. That's the life or death function in trauma cases, surgeries, and battlefield injuries. If a substitute can keep oxygen flowing through the body, even for just a few hours, it can stabilize a patient until a transfusion or further care is possible. The appeal is huge. Artificial blood doesn't rely on donors. It can be stored for months, while normal blood only lasts for around 40 days. It can withstand temperature changes, and it can be administered without matching blood types. For paramedics, military medics, or rural hospitals, that could change the game. Instead of needing access to type-matched, refrigerated donor blood, they just need a stable vial of artificial oxygen carrier. But while the idea is simple, building a liquid that safely carries oxygen through the human body is anything but. Red blood cells are biologically complex, so for decades, scientists have been trying to engineer something simpler, safer, and scalable, without triggering dangerous side effects. At a glance, blood might just look like a red liquid, but inside that liquid is one of the most sophisticated delivery systems biology has ever evolved. About 45% of your blood is made up of cells, mostly red blood cells, with smaller numbers of white blood cells and platelets. The other 55% is plasma, a yellowish fluid packed with proteins, hormones, nutrients, and waste products. For artificial blood, the target is red blood cells. Why? Because they're the ones responsible for oxygen transport, and in trauma cases, oxygen is what saves lives. Here's how it works. Each red blood cell contains hundreds of millions of hemoglobin molecules. Hemoglobin is a protein that binds oxygen in the lungs and then releases it in the tissues that need it. Think of hemoglobin like a delivery truck. It picks up oxygen in one place and drops it off in another, all while avoiding traffic jams and hazardous spills. But red blood cells do more than just carry oxygen. They buffer pH in the blood to regulate acidity, ensuring safety. They squeeze through narrow capillaries without clogging. They interact with nitric oxide to help control blood vessel dilation. And they have a flexible membrane in a donut-like shape that lets acids flow. And crucially, they do this without leaking hemoglobin into the bloodstream. Free-floating hemoglobin outside red blood cells can be toxic. It can trigger inflammation, scavenge nitric oxide, leading to blood vessel constriction, and even damage kidneys. That's where the real challenge lies. Create a synthetic version that carries oxygen as effectively as real red blood cells without triggering the harmful effects of free hemoglobin, and without needing to replicate every single function of blood. Over the decades, researchers have tried different approaches to this. Some mimic hemoglobin directly. Others looked for entirely different molecules to do the job, and each one has its own trade-offs. The quest for artificial blood really took off in the 80s and 90s. Researchers focused on two main strategies. One, taking hemoglobin out of real blood and modifying it. And two, using perfluorocarbons, synthetic compounds that can dissolve gases like oxygen. Let's start off with the first, hemoglobin-based oxygen carriers, or HBOCs. These were built from purified hemoglobin, often taken from expired donor blood or animal sources like cows. At first, it sounds promising. Hemoglobin was the key oxygen carrier in red blood cells, so why not just use it directly? The problem is that hemoglobin isn't designed to float freely in the bloodstream. Inside red blood cells, it's protected and regulated. Outside of that safe bubble, it becomes a hazard. Free hemoglobin can scavenge nitric oxide, causing dangerous spikes in blood pressure, damage the lining of blood vessels, leak into kidneys, and cause renal failure, and they have a very short circulation time, needing frequent redosing. Several companies, including Northfield Laboratories and BioPure, advanced HBOCs into large-scale clinical trials. Some showed promise in emergencies, like trauma and surgery, but others revealed serious complications, including increased mortality rates. In 2008, a sweeping meta-analysis in the Journal of the American Medical Association reviewed 16 HBOC trials and found a consistent pattern of higher death and higher heart attack risk compared to traditional transfusions. The second strategy used something called perfluorocarbons, or PFCs, synthetic chemicals that don't exist in nature. PFCs are completely inert, meaning they don't react with much of anything in the body. But they have one very useful trait: they can dissolve large amounts of oxygen, up to 50 times more than water can. The idea was to mix PFCs into a kind of liquid emulsion, which could then be injected into the bloodstream and help carry oxygen to tissues. And in theory, it worked. But there was a big catch. Unlike hemoglobin, which grabs onto oxygen and releases it where it's needed, PFCs don't bind oxygen at all. They just hold it loosely like a sponge. To make them absorb enough oxygen to be useful, patients had to breathe nearly 100% pure oxygen, often inside a pressurized chamber. This might work in a lab or a planned procedure, but it's totally impractical in emergency situations, where artificial blood is most needed. And then there was another issue. PFCs don't break down easily. The body clears them very slowly, and over time they can build up in organs like the liver and spleen, sometimes causing side effects. So while the concept is clever, PFCs never became a true replacement for blood. Despite these setbacks, both strategies taught scientists a lot. The failures weren't due to a lack of effort, they came from the immense complexity of blood biology and how dangerous even a small misstep can be. After decades of trial and error, today's researchers are taking a new approach. Instead of trying to imitate red blood cells directly, they're re-engineering how oxygen delivery works from the molecular level. It's less about copying, more about taking a new approach and rethinking it. One of the most promising developments is engineered hemoglobin inside synthetic shells. The idea is simple but clever. If free-floating hemoglobin is dangerous, why not protect it again, just like nature does? Scientists are creating nano-sized containers, often made from biodegradable polymers or liposomes, to encase purified or modified hemoglobin. These synthetic red cells can circulate safely without leaking hemoglobin into the bloodstream. The best versions mimic not just the oxygen-carrying role of real cells, but also their shape, flexibility, and ability to squeeze through tiny capillaries. Some formulations are even adding surface molecules that help these fake cells avoid detection by the immune system, allowing them to last longer in circulation. Another direction is genetically engineered hemoglobin. By tweaking the DNA that codes for hemoglobin, researchers have created modified versions that don't scavenge nitric oxide and that stay stable for longer outside of red blood cells. These versions are sometimes grown in yeast or bacteria, purified and used in encapsulated systems. And then there's the stem cell approach, an ambitious attempt to grow real red blood cells in the lab using stem cells or adult progenitor cells. These aren't efficient in the same sense. They're biologically identical to native blood. But making enough of them for real-world use remains a massive challenge. Right now, it costs thousands of dollars to produce even a single unit of blood this way. Still, the technique is advancing, and some researchers believe we may be able to produce red blood cells for transfusions within a decade. Some companies are also exploring oxygen-carrying hydrogels, injectable materials that slowly release oxygen to tissues over time. While these aren't blood replacements per se, they could stabilize patients temporarily in trauma settings or remote environments where full transfusions are just not possible. What ties all these approaches together is a renewed focus on safety, precision, and control. Lessons from earlier failures are being directly applied, like building in chemical controls to prevent nitric oxide scavenging, turning the oxygen release curve to mimic natural hemoglobin, and designing particles that avoid the immune system entirely so that they can continue to circulate in one's bloodstream. Clinical trials are already underway. One company, Hemarina, is working on a hemoglobin-based product derived from marine worms that can carry oxygen at low temperatures and with little immune response. Another, Kalocyte, is testing a synthetic red blood cells built to deliver oxygen and then break them down safely in the body. While no product is yet widely available, the field has learned valuable lessons from past failures. At a glance, blood might seem simple, just a red liquid coursing through veins. But under the microscope, it's one of biology's most intricate delivery systems. Artificial blood isn't meant to replicate every part of that system. It focuses on one life-saving role, moving oxygen where it's urgently needed. But even isolating that function is challenging, because oxygen delivery isn't just about carrying a gas from point A to point B. It's about releasing it at the right time, under the right conditions, and doing so without causing damage. What makes that so tricky is the fine-tuned behavior of oxygen transport proteins, like hemoglobin. Inside red blood cells, hemoglobin doesn't just bind oxygen, it reacts to the local environment. For example, in acidic tissues starved for oxygen, it loosens its grip and releases its cargo more readily. In healthier, oxygen-rich areas, it holds on. This dynamic response is part of what makes biological blood so effective and so hard to mimic. The real hurdle isn't just designing something that carries oxygen, it's creating a material that can sense where oxygen is needed, behave predictably under stress, and avoid harming the body while doing it. That includes avoiding dangerous side effects like blood vessel constriction or kidney damage, which happen when oxygen carriers behave unpredictably in the bloodstream. On top of that, blood is packed with other critical elements: immune cells, clotting factors, signaling proteins, and nutrients. Artificial blood doesn't aim to do all that. It's not a universal replacement. It's more like a temporary oxygen bridge, meant to buy time in high-risk settings when nothing else is available. That's why the field has shifted from copying biology to engineering precision. The goal is now a targeted tool, not a complete mimic. A material that can stabilize patients in trauma zones, battlefield clinics, or disaster sites, not by recreating blood, but by solving the one problem that can't wait: oxygen starvation. Practically, a vial of shelf-stable artificial blood isn't just a cool concept. It's a tool that could transform how first responders operate. Right now, paramedics can't carry donor blood in their trucks. It spoils too quickly, it needs refrigeration, and it requires precise blood typing. But imagine they could keep a few compact doses of an oxygen-carrying fluid right next to the bandages and defibrillator. That could mean the difference between arriving with a stable patient and arriving too late. Military medics face similar limitations. In battlefield settings, access to full transfusion support is often delayed, and evacuations can be chaotic or dangerous. Artificial blood could extend that critical golden hour when rapid intervention matters most. If a wounded soldier can keep oxygen flowing through their system just long enough to reach surgery, survival odds improve dramatically. And then there's space. On a long-duration mission to Mars, you can't pack whole blood. You can't ask for a donor. You can't rely on refrigeration. What you can bring is a lightweight powder or capsule that can be mixed on demand. NASA is already exploring options for synthetic oxygen carriers, because in space, even minor medical problems can turn fatal fast, and preparation is everything. So whether you're in a desert, disaster zone, or deep space, the goal is the same: buy time, stabilize patients, and make survival possible when traditional tools fall short. That's the real promise of artificial blood. Of course, this technology isn't a miracle. Not yet. Unresolved challenges that keep artificial blood from reaching ambulances, field kits, and space stations exist. First, there's the biology. Even the most advanced synthetic oxygen carriers can trigger unintended effects in the body. Some formulations still scavenge nitric oxide, which constricts blood vessels and spikes blood pressure. Others get cleared too quickly from the bloodstream or accumulate in organs like the liver and spleen. Managing how these materials interact with the immune system remains one of the biggest scientific hurdles. If a product provokes inflammation or causes clotting, it could do more harm than good. Then there's production. Even if a synthetic blood product works perfectly in small lab trials, it needs to be produced at scale. It must be stable across temperature ranges, easy to manufacture in consistent batches, and affordable enough to distribute widely. Right now, many prototypes are still years and tens of millions of dollars away from practical deployment. Regulatory approval is another barrier. These aren't simple drugs, they're injected directly into the bloodstream, which means the FDA and other global agencies will demand meticulous, multi-phase trials to assess not just effectiveness, but long-term safety. That takes time, and after early failures in the 90s and 2000s, regulators are understandably cautious. But even if science and safety line up, there's still one more challenge: trust. The phrase artificial blood can be unsettling. It conjures images of sci-fi experiments or chemical cocktails replacing something deeply personal and human. Some worry about unnatural substances in the body. Others fear being treated with synthetic products without full consent. And if a product is derived from animal hemoglobin, there are religious and ethical implications that need to be addressed. This means the success of artificial blood depends not just on getting the science right, but on communicating it clearly. People need to understand what it is, what it's for, and most importantly, what it's not. It's not a full replacement, it's not permanent, and it's not magic. But in a critical moment, it might just be enough to keep someone alive. And that alone is worth getting it right. The future of artificial blood won't be defined by a single product. It won't be one miracle fluid that replaces everything in your circulatory system. Instead, it will be a collection of specialized tools, each designed to solve a specific problem. One formulation might be built for field trauma, ultra-stable, injectable, and effective for just a few critical hours. Another might be optimized for surgery, delivering oxygen in tightly controlled environments without disrupting other systems. In space, powdered hemoglobin or engineered nanocarriers could be tailored for low-gravity physiology and extended shelf life. And for patients with rare blood types or transfusion complications, lab-grown red cells could provide highly customized care without relying on donors. This modular approach isn't a compromise, it's a strength. It allows researchers to tackle real-world problems directly, using the best available materials and technologies for each case. Instead of trying to replicate every aspect of blood, scientists can design precise interventions that do one job extremely well. Think of it less like creating artificial life, and more like building a medical toolkit. Toolkit that includes powders, gels, carriers, and even bioengineered cells, all tuned to restore oxygen flow when time is short and stakes are high. That's not science fiction. That's engineering with purpose. And it's already happening. Artificial blood isn't about defeating death. It's about giving life a little more time. When someone is bleeding out, on a roadside, in a war zone, on a space mission, you don't need a perfect replica of human biology. You need something that works, something that flows, something that delivers oxygen just long enough to reach help. We may never recreate what blood does, but maybe we don't need to. Maybe it's enough to build something that does one thing well: keep oxygen moving. That's what artificial blood really is: a bridge, a pause button, a lifeline made in the lab. And if we get it right, it could mean the difference between tragedy and survival in some of the world's hardest moments.
Thanks for tuning in to the Breakthrough broadcast. If today's conversation sparked a new idea, share the episode and follow the show wherever you listen. Got a question, idea, or breakthrough of your own? Reach out at breakthroughbroadcastconnect@gmail.com. Until next time, keep questioning, keep building, and don't wait for the future. Help create it.